Hi friends, today we are going to see buckling analysis of a composite plate, right? Just within a minute I will be reading the problem. A simply supported plate with the side dimensions of AX equal to 1000 mm and AY equal to 500 mm, which is edgewise loaded in compression with NX equal to NY equal to 1 Newton per mm. The plate is made up of 090 angles AS4 composite material with a fiber volume fraction of 0.6 and total thickness as 10.2 mm. The elastic properties of the lamina are E1, E2, E3, G12, G, and everything is given, and we should be computing the buckling load for the lowest 4 modes of the buckling. So for that I have opened ANSYS Classic, and I have given my working directory and my job name, and I click on run now. So okay, here we are going to analyze a simple composite plate. For that, go for preferences, set preferences to structural, say okay, go for preprocessor, element type, add, edit, delete. So as this is a composite material, we should be giving the layup. So for that, first we will take a shell element, and then we will define the layup on that same element. For that shell element, for that go add, select shell and select 8 node 281 and press OK and close. Now go to the material properties, go to material models, because we have to enter the material properties. Go to structural, linear, elastic, and it is an, as composite material is an orthotropic material, we should select orthotropic properties, and we will be entering E1 equal to somewhere around 145,880 MPa. Then E2 and E3 are 13312 MPa, 13312 MPa. Then Poisson's ratio in XY is 0.263. Then in YZ is 0.47. Then again 0.263. Then the shear modulus is 4386. Then it is 4529. Then again it is 4386. Everything is in MPa. Okay, then press OK. Then go for materials, exit. Then we have to define the layup. For defining the layup, we have to go for sections, select the shell, go for layup and say add, edit. Here if you see, if you can just see, so this is the layup which I wanted. This is the layup which I wanted. It consists of 12 layers. The total thickness is 10.2. So what happens is 10.2 divided by 12, we get an layer thickness, each layer thickness of 0.85 mm, and the thickness stacking sequence is given like this. So it means is the first layer will be 0, the next layer will be 90, and again third layer will be 0, fourth layer will be 90, and fifth layer will be 0, and sixth layer will be 90. Because here there is 3 only, we will define up to 6 layers with the 090 orientations, and then again as it is symmetric, we will use the symmetric option to create another 6 layers which are just a mirror image of the 6 layers, right? This is the final layer you should be getting. So go to ANSYS again. So for adding a layer, I will say add layer. So first of all I will add 6 layers, and I will give the each layer thickness as 0.85, 0.85, 0. 0.85, 0.85. See, everything is 0.85. Then orientation starts from 0, then it is 90. See here, in the pictorial view you will be getting an update of how the angle is, right? Then again the fourth one is becoming 90, and sixth one will be becoming 90. Now after defining our layup, we have to put a symmetric condition. For that, go for tools, say add symmetry. So you see it has added another 6 in symmetric with this arrangement. And after you finish giving all your layup, you can go for the summary, and you see the total thickness is equal to 10.2 and the number of layers is equal to 12. So everything is okay. Press OK. Then you just use this plot section option and press OK in order to just verify whether you are I have given the correct stacking sequence. See, 0 90 0 90 0 90 90 0 90 0 90 0. So we have given the correct order. Now we have to model that rectangular plate. See, it is in rectangular plate, so what happens is we can convert it into the 1/4 model for our convenience. So go for modeling, say create areas, rectangle by dimensions, and I'm going to create only a 1/4 of a model. That is why I have reduced half of the dimension in 2 directions, that is x and y directions, and press OK. So this is the rectangle you are going to get. Now we have to go for meshing, mesh tool, lines set, say pick all, and give the edge length as 25 mm and press OK. Now go for mapped mesh of that rectangular area. So we have created the mesh also. Now we have to apply the boundary condition. See, this is 1/4 model, so it is symmetric about this line, and this area is also symmetric about this line. So what we have to do is, first of all, we have to specify the symmetric conditions. Go for the loads, define loads, settings, and apply structural displacement, symmetric boundary conditions on lines with areas. And first of all, select this line, press OK, and select this area, press OK. So you applied a symmetric condition of this area about this line. Now you have to put the same condition about this line. So for that, again you select with area, select this line, press OK, and select this area, press OK. So you have placed both the symmetric conditions about the 2 lines. If you want to verify it, you can just go for the list, go for the loads, DOF constraints on all lines, and you can see on the line number 1 and 4 you have given symmetric about the area, right? Then we have to apply a pressure load. Or first of all, I will apply the constraint, then we will go for pressure loading. So displacement on lines, and you have to fix this line as well as this line, because it is a simply supported beam, simply supported condition. We will just fix uz to 0, press OK. So we have constrained uz here. Now we will go for the pressure, say on lines, and select these 2 lines, press OK, and give a value of 1 Newton per mm, right? So we have applied the required pressure and everything. Before just solving the problem, go for solution controls, and say calculate pre-stress fx, press OK. Now you solve the problem. Current load step, solve. Okay, solution done, right? So we have performed a static structural analysis. Now only we can, after performing a static structural analysis only, we can perform a buckling analysis. For that, go for analysis type, say new analysis, and then press select eigen buckling, press OK, and then go for the solution analysis options, and here you can choose the mode to extract. We'll leave it to black Lancos, and I want to extract 4 modes. So I press OK. I have entered 4 and press OK. Now what I will do is I will go for solve, say current close step, say OK. So the solution is done. And now you can see, go to the general post processor. In the read results you say by pick, and here you can see 4 types of load steps, 4 types of steps, right? These are our 4 types of sub steps. So the first one, so we have so we can also animate the we can also read the results from different time steps or sub steps. Say read, and you can also plot. You can just see the deformations by going to plot results, say deformed shape, press OK. And here you see this is a factor, that is the buckling factor. When you apply when you multiply the buckling factor with the length of that dimension, then you can get the total buckling load. For example, in the set number 1, if we see buckling load factor is 209.43, and when it is multiplied with 500, you will get 104,715 newtons, which is the actual buckling load in newtons. Then again, if you see for the second set, say this is for second set, right? So if you see, you can just multiply this 640.43 into 250, and you will be getting somewhere around 107.5 newtons, which is a buckling load, right? Okay, so with this we will finish this tutorial. Okay, thank you, bye.